I want to show you how to plot a linkage disequilibrium heat map, and this is going to be helpful to those who are doing GWAS. And when you are doing your association studies and you get heat maps in the on the Manhattan plots, and then you want to see the resolution of your association studies, and this is done by looking at the linkage disequilibrium heat map on the regions where the heats were found. For instance, if you found that there were heats in chromosome 1, you may go ahead in those regions or positions of those SNPs and plot a linkage disequilibrium heat map. And this is going to help you see the resolution of your association if those SNPs are in a linkage disequilibrium with the gene of our interest. That's the importance of plotting the linkage disequilibrium. I'm going to make life easier by going directly and showing you the easiest way to plot this. What you need to know your SNPs that were the name of the SNPs that were significant. And again, the second thing you need to have is the data on the chromosome, the the chromosome number where you had your hits, and also the positions of the chromosomes of the SNPs in that chromosome. Let us load this data, the data that we used to do association studies. We import it and call it gdot. Because this is Heatmap data, we need a numeric data. This Heatmap, we need to convert this into numeric data. But first, let's assume that chromosome 1 had hits. We have to subset this data into chromosome 1 and then convert that data into numeric data from Heatmap data. I use Gapit to do that. We have so many packages you can use. You can use Sinipredi and others, but I like to use Gapit because it gives me map data and also it gives the numeric data. So we need to subset our data and get only chromosome 1 because we got hits in chromosome 1. So we have subset this data and extract only chromosome 1 and then name it G.1. After that, we use Gapit to convert this HubMap data into numeric data. We do that. We wait, give it time to run. That done. Next, in the numeric data that we have this week, we call it the .n. When we open this is the map data, and this is the numeric data GD, and this is the hub map data, and this is the kinship. We are interested with these two GD and GM. Now we need to extract first GD and then run. We are extracting GD and we are going to remove column 1 because it has the allele data which we don't need, and then convert this numeric data into a matrix and call it geno. Now we have the numeric data. Now we need a map data, which is GM. We extract it like that and call it map 0. Good. Now we need to see the dimension of geno data and the map data. It has to have same number of SNPs. Here, this is the same number of SNPs, and these are the same number of SNPs. We want to convert this geno into a SNP matrix object. You use SNP stats, load SNP stats, convert this geno, which was numeric, into a SNP matrix using this SNP stats. We need that done. And now we need to get the position from the map. You see, we only need to get the positions. This position here. We need to get it. We call it GDIS. You can give it any name. We have done that. Then we use this function LD Heatmap from a package called the LD Heatmap. LD Heatmap package has a function called LD Heatmap. So we loaded the package into our library. But we use this function and we use this SNP matrix object, and also we use our positions SNP position as genetic distance. Then we give it maybe a name. You can give it a name, anyone which you want. I call it my heat map. Run that. It's going to take some minute. Now, after running this, we got our heat map. It's here. Let me zoom it. So this is our heat map. And for us to see, you can see that we have r squared, pairwise r squared. As you move from 0 to 1, the darker it becomes, it means you are having a strong linkage disequilibrium. The lighter it is, the r squared is 0. Let us tweak this plot a bit, a little bit, so that we can make it beautiful to interpret and easy to interpret and see. We can identify the names of the SNPs that were had hits. You see, you use the negative log 10p. Then you filter that according to the threshold which you placed in your Manhattan plot. There are p values in the US SNP data. Then you take negative log 10 of those p values, and you get to the threshold, and anything which is above the threshold is your significant SNPs. You get the names. These are the names which we got. So we are plotting the LD heatmap. We're using LD heatmap, but now we are going to plot this my heatmap here. This my heatmap. We are going to modify it, my heatmap. But again, we are going to include the SNP names. These are the SNP names that were in linkage disequilibrium with our trait of interest, and then we give it a color, which is we have given the heat dot colors number 15, and then you run that. So it will give us the name of the SNPs, the location where they are, and also change the color to heat map, to heat colors. Right. Good. You can see now we have our SNPs. They are here in color blue, and the color of this heat map has changed. The more red it becomes, the stronger the linkage it is. So one last thing we can do, you see this name is so small. We can adjust its size. So we are going to use this grid.area. We are going to use this function to change the size of our SNPs, and the size is here 0.8. Use this function. We use SNP names, gene map, LD heat map. So to edit this, first of all, after drawing this, that's when you change this. You don't start with this. We run that. Good. You can see that the size of our SNP, the name SNP name, has increased. So you can zoom. After zooming, you can see that we have adjusted the size of the SNP name, and also you can see that the plots now can be well read and see the positions of your SNP of interest. You can now see the resolution of your association mapping. I want to say that this is a very heavy task. On a normal PC, it's going to take some minutes. You can't plot the whole genome using this technique, and this is a technique used if you want to see the whole genome, but this one is suitable for only seeing maybe one chromosome or a particular region of interest. It's not good for the whole genome, which is it can do, but then a normal PC cannot handle this. A normal PC will take some time to handle this. Thank you. I hope it's helpful. If you need more information, you can contact me.